Hello, and welcome to study our favorite course, sensor and instrumentation. So today we will be continuing to study optical sensors, and from the beginning, I want to say that measurement of force and torque is mostly based on measuring the resultant deformation. It may be as compressive as tensile strain. In this sense, in principle, the displacement sensing methods discussed in previous section of this lecture and are as a candidate in the selection process of a force measurement method. The typical application, however, justifies a separate section on these kind of measurements. An applied torque results in a twist of the object, for instance, a shaft, over the angle of phi. You may see here on vertical plane. This angle is about proportional to the torque and can be measured in various ways. To obtain a high sensitivity, the distance between the end points should be large. However, this may impede accurate measurement of the relevant rotation. A simple solution is to transfer the rotation at the one end by a mechanical extension to near the other end. Look at the figure A on the left part of this slide. And simplifying the angle measurement, when the object angle is still too small, an elastic element with non-compliance can be inserted as shown in figure B on the right side of this slide. The torque is reconstructed from the relative angle between two end points of the rotational spring element. A special challenge is to measure torque on rotating shaft. In such an application, contact-free sensing is required, which can be realized by optical means. This method is used for torque measurements on a wood cutting machine. The discs in this figure are provided with optical markers on the circumference, viewed from the side by a pair of photodiodes. Even at a cutting speed of 24,000 RPM, a proper torque signal could be obtained. Another particular application of an optical force measuring system is the online measurement of two-dimensional force on a pen for the purpose of signature verification. The force on the pen tip is transferred to the other end of the ink channel, which can move relative to the pen holder. A small mirror mounted on the end side of the ink channel modulates the direction of the laser beam, falling on a count photodiode. From the 4 photocurrents and 2D horizontal force on the pen tip can be reconstructed. Since the transfer from the force via mirror displacement to the photocurrent is rather complex, the device needs to be calibrated. Experiments prove the feasibility of the optical method. And very small deformation are best measured by interferometric method. And this principle enables displacement measurements with very high resolution. An example is the study on electrostrictive properties of particular material. Electrostriction is electric field induced strain. Deformation are in the subangstrom to submicron range. Industry presents a laser interferometric system that is able to measure such small displacement. The paper reports a displacement resolution of less than 10 nanometers, and operates in a frequency band from 3 to 20 Hz. Many more examples of optical or interferometric force and strain measurement systems have been reported in various literature. A particular kind of force sensor is a tactile sensor, mainly encountered in robotic applications. Tactile sensors of the cutaneous type consist of an array or matrix of elementary pressure or displacement sensors. Many optical techniques have been developed to obtain information on the displacement of the individual element or texels. Four major methods are variable transmission, variable contact area, total inertial reflection, and pressure-sensitive optical fibers. A common problem is the resolution. In order to realize high resolution, the texels should have small dimensions and be densely packed. The principle of variable transmission is illustrated in this figure, namely on the figure A. As with almost all tactile sensors, the applied force is transferred into a displacement by an elastic layer. In the variable transmission type, the displacement is measured by mechanical modulation of the intensity of a light beam, a method already published in 1983. The commercial device has a resolution of 16 times 10 tactile elements and pitch of about 0.3 centimeters. Despite this limited resolution, the sensor is shown to be suitable for object recognition by touch. The principle of variable constant surface is already addressed earlier, where the contact area is measured by resistive means, but optical readout is also an option. The variable contact area is achieved by protrusions at the backside an elastic sheet, mounted on a flat transparent plate that serves as a waveguide to illuminate the elastic sheet with the bubbles. Upon the applied force, the bubbles are impressed and the contact area with the glass plate increases, as you can see on a figure 15. This change in area is measured optically by a camera viewing the back side of the plate. The resolution of this tactile sensor is restricted by the number of elastic bulbs. The camera is not limited with respect to the resolution. However, it makes the sensor rather bulky and unsuitable for incorporating in a robot gripper. An advantage of this setup is that scanning is performed by the camera electronics, hence the speed is high. A flatter construction can be achieved by crossing optical fibers. The structure is similar to that of the carbon fiber tactile sensor. The crossing point acts as a texel, and the fiber performs the scanning. When a force is applied to such a crossing point, the transmission of both fibers alters due to microbending. These fiber optic tactile sensors have a potentially high resolution, but more research is required to fully profit of this property. For less demanding applications, for instance, variable sensing, they offer good prospects. Measuring the 3D position of a particular point is a rather common task in mechatronics. For instance, the position of the stage in a coordinate measurement machine, and robotics, the position of the end of effector or an object in the robot's environment. In many applications, a further task is to track the side object or a specific point on that object when it is moving around. In general, two different approaches can be considered: imaging and active lighting, such as with triangulation. The latter approach is characterized by the presence of a light source with known position in the system coordinate frame, and that this position is used to reconstruct the position of the object. Vision systems having environmental lighting do not have that information and require some kind of calibration to reconstruct the object position from one or two-dimensional projections of the scene on the camera chip. It should be mentioned that active lighting systems may also comprise a camera, like line, matrix, and 2D PSD. However, the object that is looked for this illuminated by a known light source, such a laser spot, or laser line, a pair of lines, or a 2D light pattern, also called structured light. The reconstruction process combines knowledge about that light source and the image of the reflected light. Tracking by vision is a topic on its own and will not be discussed further. And somebody who interested in this may refer to the extensive literature. And this table compares both concepts with respect to some important design considerations. Tracking systems using a special light source can be configured in various ways, depending on such systems' classification as power consumption, available space, and environmental conditions. Since the transmitter usually takes the most of the available power, the choice between putting the transmitter or the receiver on the moving object is an important piece. Further, there is the choice between direct mode and indirect or reflecting mode. The latter has the advantage that the object to be tracked is completely free from wiring and power sources. Only a distinctive indicator should be present, detectable by optical system, for instance, a light spot, a light pattern, a black and white marker, and a retroreflector, or something similar. When the design is based on the direct mode, again, various options are open: transmitter on the moving object and a receiver somewhere in the environment, or vice versa. Further, since the object has to be tracked, either the receiver or the transmitter should be able to explore the environment by some kind of scanning. Of all possible combinations, practical applications can be found. At startup of the tracking process, the object position is usually not known. Therefore, first a search is performed, in which the environment is scanned by either the transmitter or the receiver, until the receiver gets a proper signal back. Once the object has been found, a tracking algorithm controls the transmission path to follow the movement of the object. Further details of the system design strongly depend on the specific application. As an illustration, a few examples will be described. A first application is the 3D tracking of the end effector of a robot. Usually, the position and orientation of the two center points, or so-called TCP, is derived from the position of the joint. However, errors in the mechanical construction and the compliance of the composing parts cause errors in the position of the TCP that may obstruct accurate positioning of the end effector. Measuring the TCP with respect to the robot coordinate frame may provide data for compensation for such errors. A well-known approach uses a light source mounted on a suitable place near the TCP, emitting light in all directions. The light is perceived by a set of cameras like 2D PSD with CCD matrix, positioned at fixed known locations, together covering the full workspace of the robot. By coordinate transformation or triangulation, the position of the TCP can be reconstructed from the spot positions in the image plane. The working range is set by the reviewing field of the camera. This basic idea can be implemented and extended in various ways. The principle of feedback may be applied to enhance accuracy and increase the working range. This is achieved, for instance, by mounting the camera on a rotatable platform. The orientation of the camera is controlled in such a way that the spot is always in the center of the image. In this application, a 2D and PSD camera is a good choice because only a single light spot has to be detected. Since the spot is always in the center, errors due to the nonlinearity of the PSD occurring mainly at the edges of the device are limited and eliminated. Encoders on the axis of the platform provide the information about the light source position. To find the orientation of a particular part of the robot, 2 or more light sources may be placed on the construction, viewed by 1 or more cameras in the work coordinate system. In all cases, the system, once set up, must be calibrated to obtain the highest accuracy. In an alternative approach, to find the end-up effector position, the light source and detector from the previous example are interchanged. The sensor or camera is mounted on the end of effector, and a source transmits a light pattern into the direction of the sensor. The pattern can be a light spot, a line when emitting a light plane, a crosshair, or any known pattern. A 2D pattern, in combination with a matrix sensor, allows the measurement of the position and orientation. An algorithm to obtain the required information dealing with the measurement of the end of effector position. Tracking systems are also used in rehabilitation to study the movement of the people. Here, the reflection mode is common practice to minimize movement restrictions for the test person. A set of reflecting pads or spheres is positioned on specific location on the body, like arms, legs, head, shoulders, and feet. These makers are illuminated by a specific light source, for instance, infrared, while the reflected light is viewed by a set of cameras. To increase the SN ratio, the light is first filtered so the camera actually sees mainly the reflection from the markers. Since not all markers can be seen at the same time due to occlusion by the test person, and since all markers are identical, spatial tracking algorithms have been developed to identify the tracked body part. Accuracy requirements are not severe. Processing speed is a more important issue since fast movements must be tracked and analyzed. In highly accuracy applications, for instance, coordinate measurement machines, interferometers can be deployed to accurately measure the position of a machine part. Tatsuji et al. Described a tracking system for the coordinates of a stage. It comprises a retroreflector mounted on the stage and four lasers that track the position of the retroreflector. A special algorithm has been developed to reconstruct all three coordinates. The fourth, redundant laser is used for self-calibration. An interesting application of an optical sensor for 3D orientation tracking is the integrated optical sensor used in a handlehead controller or human interface device for the V timing console shown in this figure. Besides main use as key input device, the sensor has also found use in mechatronics. The sensor uses a 3D 2D imaging sensor to detect infrared dots. With two dots at a known fixed distance, it is possible to determine both orientation and distance with respect to these dots using triangulation. In the VNO application, this optical data is fused with data obtained by a MEMS gyroscope and accelerometer in order to obtain an accurate position and orientation estimate. A related implementation of motion tracking using a low-resolution imaging sensor is the optical flow sensor, which is deployed in an optical mouse, shown schematically in this figure. An LED, usually namely red LED, is used to illuminate a scene, like surface of a desk, that is captured with the imaging sensor. These sensors typically have a very low resolution, like 19 times 19 pixels, not to obtain a full image, but to measure a shift in pattern caused by displacement. This pattern shift is detected and communicated to the hardware the mouse is connected to. These types of sensors and the optical flow principle in general are used in mechatronic applications, such as assisting vehicle navigation. The shape of an object is characterized by the coordinates of its outer surface. Measuring the shape is useful in lots of applications. For instance, localization and orientation of the object in a special coordinate system, identification of objects, quality inspection, and parameter extraction. The accuracy requirements are set by the application. The highest accuracy is needed in product inspection, where some mission resolution is often required. Identification and characterization are fewer demanding applications. The transmission mode is the most simple and effective way to control production processes and to monitor the dimensions of product. The applicability of the method is almost unlimited. The aim is the online determination of the rotor pallet diameter up to several meters with an error less than 10 micrometers. Light source and detector a quad photodiode, are positioned just at the outer edge of the blade. A small change in diameter modulates the transmission, yielding information about the error. An illustration of the object characterization using distance sensing with fiber optics is the measurement of two wells. In this intensity-based method, light to and from the tool, here a milling device, is transmitted by a bundle of fibers. A group of fibers in the bundle transmits the light towards the object. Another group transmits the reflected light to the sensor unit. Basically, the distance to the tool is measured according to the principle shown in this slide, while rotating an online plot of the distance is made. This plot provides information about the wear state of the tool. In this application, the intensity method is satisfactory because the setup is fixed, the distances are short, and the environmental conditions are more or less constant. For more accurate numerical shape data and for applications in a less structured environment, the intensity method is usually not adequate. We discussed two other modes, probing and triangulation. Many 3D coordinate measuring instruments are based on a touch probe, with which the contours of an object are followed to obtain 3D shape information with high accuracy, also referred to as dimensional metrology. The touch probe consists of a ball-shaped touching point with well-known dimensions and which is connected to the end of a stylus. The probe is moved by a set of actuators until it touches the object. Next, the movement is controlled in such a way that the point follows the surface of the object, thereby just keeping contact between probe and surface. The measurement quantity can be the force on the ball, the bending of the stylus, or the displacement of the ball relative to the base of the system. Shape information is reconstructed from the momentary positions of the stages and possibly corrected for the bending of the style. Various experimental setups of the latter approach using optical sensing, where the changing position of the ball at the end of the stylus is measured by a couple of optical fibers. The ball is elastically attached to the end of the stylus. So when the probe touches the object, the ball is displayed somewhat in the direction of the reaction force. Further mirrors are connected at the top of the ball. They follow the rotation of the ball when touching the object. A set or a bundle of fibers is fixed to the stylus with their ends just above the mirror. According to the principle of this figure, the ball movement is measured in two directions, normal to the stylus. Ball deflection down to 1 micrometer, corresponding to a sideways force less than 1 millinewton, and can be radially by measure. In less demanding applications, or when touching is not possible or allowed, triangulation is a suitable method to obtain shape information. For shape information, the triangulation configuration from this figure should be extended by a scanning mechanism to cover the whole area of the object to be investigated. The method is based on measuring the distance from a specified point to the surface of the object in straight line. The method is also referred to as a ranging. Evidently, due to self-occlusion, only that part of the surface that is in indirect side of both the transmitter and the receiver can be investigated. Optical range finding, some call it 2.5D imaging, is also frequently applied in robotics. For instance, to obtain information about the robot's environment for navigation purposes, automatically guided vehicles, and many other tasks. Navigation by ranging is discussed in the next section. For shape measurements, the most straightforward configuration is a 2D point scanning. Also, you may see on a figure A on the top of this slide. The range distance is determined for each individual same sample point by triangulation. Needless to say, this is a rather slow acquisition process. The fastest solution is line scanning according to the figure B. Instead of a point, a line is projected onto the object. The line is created either by the special optical lens or by a fast rotating mirror and is viewed by a matrix camera. The line is mechanically scanned in the perpendicular direction to cover the whole surface of the object. If the object itself is moving, as on a conveyor belt, such scanning mechanism may be unnecessary. This shows the basic setup of a line scan range finder. In this simple configuration, the line is created by a rotating mirror. The projected line follows the shape of the object. This pattern is viewed by a camera. From the known positions of the mirror, the light plane and the camera, the shape of the intersection between the object and the light plane can be reconstructed. In general, not all points of the object are illuminated, and not all illuminated points may be viewed by the camera. Those shadows prohibited capturing the whole cross section. When this is not acceptable for the application, a second triangulation system can be used operating under a different angle. Another applicable option is a set of a mirror through which the scanning plane, transmitted by a single source, is projected from the two sides onto the object. The same mirror can be used to redirect the light from two sides to the common receiver. This solution is proposed in, for instance, in which the scanning is performed by a optic deflector. Evidently, the two scans should be complementary to build up a complete image of the object. A similar solution with two mirrors. In this example, elliptical mirrors are used, which allows dynamical reconfiguration of the geometry. And this results in a better depth resolution and reducing occlusion effects. And finally, we mention a laser range finder that uses a multi-facet pyramidal mirror. This mirror acts as a double scanner, one of the transmitting beam and one for the reflected beam. Much research is being done to monitor the condition of buried pipe. Inductive and magnetic sensors, magnetic methods have been discovered, but optical systems are being developed as well. Pipe robots carrying various sensors travel through the pipes under the test, collecting important data about the pipe's condition, like obstacles, corrosion, leaks, and mechanical defects. The smaller the diameter, the more severe and the more requirements with respect to size, power efficiency, battery power, and cost. As an example of an optical test system for small pipe diameter, this work concerns an optical system that measures the inner surface of a 10 mm part. The sensing system consists of a laser, a scanning mirror, a motor, and a PSD auxiliary assembled to fit inside the part. The system enables the detection of surface deflects as small as 0.1 mm by means of triangulation. Mechanical scanning is relatively slow and forms the major limitation of the acquisition time, in particular for a 2D scanning mechanism. Line projection using cylindrical optical considerably reduces the acquisition time and is therefore widespread in range finding systems. One solution to speed up scanning of the other dimensions is an array of transmitters sending a set of parallel lines to the object under the test. The resolution is limited by the number of transmitters, which for practical reasons cannot be very high. This solution is only suitable in cases where no high resolution in the scanning direction is required. A limited number of parallel lines are projected onto the object. The cross-section of each line has a bell-shaped intensity distribution, and the lines overlap partially. When two adjacent lines are transmitted simultaneously to the total intensity of the projection shows a peak at a position that depends on the relative intensities of the individual lines. By controlling this ratio, the peak value shifts across the object under the test over a distance about equal to the line separation. The range can be extended simply by adding more lines. Based on this principle, an acquisition time of 6 microseconds was obtained with a spatial resolution of 1 micrometer over a scanning area of 22 times 24 millimeters. Measuring the shape of very large objects can also be performed by optical ranging. Since the distances involved in such application are much larger than in the previous example, triangulation is not a suitable technique. Ranging using optical TOF is a better option. Moreover, to keep the sensor dimension small, a feedback approach with tracking is recommended. An example of this combination, TOF and tracking. The system has a tracking accuracy better than 1 millimeter and a measurement resolution is the same order over a working distance of 12 millimeters, 12 meters, and angle range plus minus 45 degrees. Another application area concerning acquisition of shape information is the determination of a high profile or depth profile. For instance, in SIM tracking for automatic welding. A specific example of a high profile measurement where methods for recognition of electronic components on a PCB are studied. One of these methods is based on triangulation to obtain 3D shape information about classes of components, like ICs, capacitors, batteries, and so on. Also, here the object, PCB, this component, is illuminated from two sides to eliminate shadow effect. Instead of one line, a sequence of line patterns is projected on the PCB, which is viewed by a single camera. From the obtained range data, the shape of the relevant parts in the image is reconstructed and parameterized to match them with the corresponding parameters of standard electronic components. One of the limitations of resolution in a structured light system with lines or with other patterns is caused by the line width of the projected light. Several researchers have proposed methods to reduce the resolution by using special image processing algorithms. Examples can be found where the shape of trees is determined using triangulation, in which the obtained improvement of the resolution is illustrated by the shape measurement of a car tire. As objects are normally tested on the base, the bottom side is not accepted to the triangulation system. For regular objects having a flat bottom, this is not a problem. Recovering the full shape of irregular objects, like agricultural products, is not possible in this way. The sensing system consists of a ring with a large number of transmitters and receivers located alternatively around the ring and pointed inward. The area inside the ring is scanned by successively activating the transmitters. The light from each transmitter is detected by all receivers simultaneously. When an object resides in the ring, some of the receivers are in the shadow of the object and will not receive light while the other do. By cycling along the ring, a set of chords is obtained approximating the shape of the object, actually only in the cross-section with the plane of the ring. When the object moves through the ring, just by following, a 3D image of the total shape is obtained. The method is cheap and simple and appears to be suitable for characterizing the shape of potatoes and similar products. In many robotic applications, structured light systems using random patterns are being used, which have originally a different application area. Microsoft designed an input device using a 3D scanner based on structured light for their Xbox gaming console called Kinect, as shown in this video. Because of the versatility, availability, and price range, these sensors have been applied in many robot projects, especially projects in a social setting. The Kinect sensor projects an infrared point grid onto a given scene. This scene is captured using a normal visible light camera, as well as a camera sensitive for the infrared spectrum. Both image sources are combined to recreate a 3D model of the captured scene. For human motion and position detection, part of the recreation in software is aided by using skeleton models to predict human stances and moves. One of the earliest applications of optical sensor in robotics is possibly the robotic eyes in the moving creatures by Sir William Gray Walt. The robot Ilse, shown in this figure, uses a photoelectric cell to locate its charging station. The similarities with its modern counterparts, such as the Roomba vacuum cleaners, are striking. These modern vacuum cleaner robots still use optical sensors for detecting obstacles and driving back to the charging station. The control principle has been elaborated by Valentino Breitenberg in his famous Beatles, where a cross-link between two hypothetical models and sensors makes these vehicles track a light source, shown in this slide. Part of a practical implementation of the ideas of Breitenberg can be recognized in a flavor of robotics called BEAM robots. BEAM standing for biology, electronics, aesthetics, and mechanics. This style of building robots has been initiated and propagated by Mark Tilden and others. The robots use similar principles to stay alive, and others say to locate the brightest spot in the room, to use a tiny solar cell for recharge, while at the same time avoiding obstacles. An example of a robot inspired by these principles is given in this figure. Line and area cameras are often encountered in robotics for the purpose of object recognition, environmental exploring, navigation, and robot calibration. However, we will not discuss these applications further here. The person who is interested in these more details is referred to the extensive literature on computer vision. Color information can be very useful in a number of applications, such as for painting robots, object sorting, for recycling purposes, and so on. A color camera is a suitable transducer, but when no spatial information, but just color is needed. A simple set of 3 diodes with color filters will do as well. Movement is change in position, and hence it can be measured by any position sensor, provided such sensor has an adequate range and response time. When the movement is beyond the range of a position sensor, for instance, as may occur with moving robots and AGVs, other sensing techniques to capture the position are required. A simple optical navigation method is tracking a marked path. The path may consist simply of a contrasting line on the floor. An LED or other light emitter casts a light beam down to the floor, and 2 detectors on either side pick up the reflected light. The vehicle is controlled in such a way that both detectors receive the same light intensity. In other words, when they are equal distance from the reflecting light. When the vehicle starts to deviate from the track, either the left or the right detector receives more light, from which a control signal is derived. When also the position of the robot or vehicle along the path must be determined, the path can be coded along the track, for instance, by a continuous pattern of light and dark fields, or particular optical codes. Similarly, the movement of a free mobile robot can be tracked by some contrasting 2D patterns on the floor, using sensors detecting dark light transitions, or even an onboard camera viewing the floor. Another possibility to measure speed makes use of the natural irregularities of the floor surface. At 2 positions of the vehicle, front and rear, the random intensity variations are measured. The speed follows from correlation of the 2 random signals. Absolute position is then obtained by data reckoning techniques, starting from a known position and possibly updated from time to time with reference positions achieved by special markers or beacons. Beacons for the determination of absolute position can be either passive or active. Passive beacons are, for instance, reflectors located at precisely known positions. The transmitters and receivers are located on the beacon. Active beacons transmit signals that are received by the beacon. Important design considerations are the directivity, or the scanning area, of the transmitter and receiver, the location of the beacons, and the identifications of the beacons. The beacon must be able to recognize the active beacon. An example of a mobile robot using 3 active beacons. The sensing system on this robot measures the angles between 2 beacons paired, alpha between B1 and B2, and beta between B2 and B3. Let's look at this figure, please. Then, the robot must be located at a point P, lying on the crossing of the 2 cycles C1 through B1, B2, and P, and C2 through B2, B3, and P. From the known beacon position and the 2 angles, point P can be calculated. The sensing system on the robot consists of a rotating photodiode, 4 turns per second, connected to an encoder that provides information on the angle of the optical axis with respect to robot coordinates. During one complete turn, the detector receives 3 consecutive signals from the beacon, from which the angles alpha and beta are derived. The light from the beacons contains a unique code to distinguish them, which is decoded by the sensing system. The resolution of this angle measurement is better than 0.005 degrees over a distance range from 1 to 10 meters between robot and beacon. Obviously, the system just described requires a direct sight of view between beacons and beacon. In many applications, this is not the case. For instance, when AGVs have to native in a complex area with many large obstacles or in a corridor. Placing beacons in the plane of the AGV could be complicated, expensive, or even impossible. A solution could be a higher position of the beacon, for instance, on the ceiling of a car, and thus increasing the working range of the beacons. Since the beacons and sensors are not in one plane anymore, however, this complicates the optical configuration and the triangulation algorithm. The SECPA gives a solution to this problem, based on a special optical scanning system able to accurately measure angles as well, resulting in a position accuracy better than 2 millimeters in a range over 2 meters, 10 meters. Navigation can also be performed by a simple 2D PSD camera. When an extra degree of freedom is allowed, the 3D position can be derived with 2 such cameras. From the output of both 2D and PSD cameras, the 3 coordinates like XP, YP, and ZP of the light spot can be calculated, as illustrated in this figure. The focal point of the left camera coincides with the origin of the reference frame, so the light spot has coordinate XD1, YD1, and minus F1, which satisfies the first equation here on the top of this slide. The second PSD camera is rotated over an angles P and theta around the Z and Y axis respectively. The coordinates of the light spot with respect to rotated PSG are related to that of the reference frame according to the transformation formula, as you can see here in the second expression on the middle of this slide. When the camera is further translated over a vector of xt, yt, and zt, the coordinates of the light spot satisfy the expression here on the third equation on the bottom of this slide. And with this position, the light spot can be expressed in terms of the output coordinate for both PSD cameras, the location length, and the geometrical parameters of the system. If only speed information is required, inertial sensing techniques can be applied. Integrating the output of an accelerometer provides linear velocity. A gyro gives the angular rate. Most optical gyros are based on the interferometry. An extensive overview of commercially available optical and other gyros. And now we will start to study another interesting topic called piezoelectric sensors. In this lecture, in this part of our lecture, we discuss principles, properties, and applications of piezoelectric sensors. A description of the piezoelectric effect is followed by an overview of the most common piezoelectric parameters. Piezoelectric materials are used in force sensors and accelerometers, the subject of the second section. Interface circuits for piezoelectric sensors are treated next, and various specific and original applications, including tactile sensors, are listed in the last section of this part of the lecture. Piezoelectricity is encountered in some classes of crystalline materials. Deformation of such materials results in a change in electric polarization. The position of the positive and negative charges in the crystal are displaced relative to each other, causing a net polarization or change in intrinsic polarization. This shows a simplified 2D representation of this object. In Figure 8, the structure is fully symmetric. The center of gravity of all positive charges coincides with that of the negative charges. The whole crystal is electrically neutral. When compressed in the horizontal direction, like in Figure B, the center of positive charges has shifted downward, resulting in a non-zero polarization. In case of a vertical compression, like in the Figure C, the center of positive charges has shifted upward, resulting in a non-zero polarization in the other direction. This shift of positive charges relative to the negative charges produces opposite charges on the opposing surfaces of the crystal. Evidently, this figure is a strongly simplified representation of the piezoelectric phenomenon. Crystal structure, addition of dopants, and other treatments of the material substationally determine the piezoelectric property. For instance, one project shows the charge displacement for various compositions of PZT, lead zirconium titanate, and particular piezoelectric material. The surface charge per unit area is proportional to the applied stress. The charge is proportional to the applied force. Generally, the material is shaped as small rectangular blocks, cylinders, plates, or even sheets, with two parallel faces that are provided with a conductive layer. The construction behaves as a flat plate capacitor for which Q equals C times V, so the output signal is available as a voltage. The sensitivity of such piezoelectric sensor is characterized either by the charge sensitivity as proportional Q over F, or by the voltage sensitivity proportional V over F. The piezoelectric effect is reversible. It means a voltage applied to the piezoelectric material results in a small deformation, the converse piezoelectric effect. This property is used in piezoelectric actuators. The following groups of materials exhibit piezoelectricity. And first, natural piezoelectric materials. A well-known example is a quartz. It means like crystalline silicon or ceramic materials or polycrystalline, for instance, barium titanate, polymers, for instance, PVDF. Natural piezoelectricity was discovered already in 1880 by the brothers Curie in several crystalline materials. The most known is quartz, crystalline silicon dioxide. It has a rather low but stable piezoelectricity, about 2 picocoulomb per Newton. Materials of the second group contains electrical dipoles, but are not piezoelectric, because the random orientation of the dipoles average out, resulting in a zero net polarization. However, they can be made piezoelectric by pooling. The material is heated up to the so-called Curie temperature, where the dipoles obtain high mobility. In this state, a strong electric field is applied during a certain time period, and the dipoles are oriented in the direction of the field. After slowly cooling down, the dipoles maintain their orientation, giving the material its piezoelectric property. Compared to quartz, cold ceramic materials have a much higher piezoelectricity, ranging from 100 up to over 1,000 picocoulomb per meter. The orientation of the dipoles slowly tends to a disordered state, resulting in a negative exponential decay in sensitivity over time at this equation. And you can see on the curves on the bottom, where the S from T and S from T naught are the piezoelectric sensitivities at time T and at the end, and the polarization treatment time T naught. The factor C here in this expression lies in a range between -5 in times the 10 in -2 to -5 times the 10 in -3 per decade for the room temperature. For this reason, the pole material is aged artificially before being applied as a transducer. Mechanical and thermal shocks, however, may initiate new aging effects. Clearly, the decay goes faster at higher temperature. Note that even quartz loses its piezoelectricity above the Curie temperature, which is 573 centigrade. In 1969, researcher Kawai discovered that some polymers can be made piezoelectric by pooling under particular conditions. The most popular piezoelectric polymer is polyvinyl fluoride in a chain of repeating units CH2 and CF2. The material is available in sheets with various thickness, from 6 up to 100 microns. PVDF has the highest piezoelectricity of all known polymers, and it's have about 25 picocoulomb per meter. Polymer is performed during stretching in one or both directions to obtain a reasonable piezoelectricity. Piezoelectric has a limited temperature range because its melting point is about 150 centigrade, whereas the Curie temperature lies around 125 centigrade. Since shortly after the material became commercially available, the material has been successfully applied as a transducer in the thermal, mechanical, and acoustical domains. An additional advantage of PVDF over ceramics is the compatibility with silicon technology. The thin sheets can be glued on top of a silicon wafer that contains part of the interface electronics. More recently, piezoelectric copolymers of PVDF, for instance, VDF or TRFE, have been developed, and this material is available as a solution. It can be deposited on the wafers by spinning. Polymer on silicon technology opens up the possibility for the creation of smart or integrated sensing devices for the detection of pressure, force, sound, and thermal energy. The latter due to the fact that PVDF is a pyroelectric as well. The major advantage of polymers over ceramic materials is their flexibility and small size, sheet thickness of several micrometers. Another development concerns the deposition of thin film ceramics. This technology too can benefit from compatibility with integrated circuits and using the reversibility of piezoelectricity for microactuators. The primary output quantity of a piezoelectric sensor is charge. A bit later, we will show two basic schemes to convert the charge into a volt with a very high load impedance, like open terminal, and with an almost zero load impedance, short circuit terminals. In literature, piezoelectric relations and properties are described in several ways. In this lecture, we use the two-pore description, which is analogous to the description of electrical two-pore. Let's look at this figure, please. Two pairs of variables are involved. Two inputs variables on the left side and two output variables on the right side. Each pair consists of one extensive and one intensive variable. The relation between the four quantities can be described in various ways. For a linear electric network, we can express the two voltages as a linear function of the two currents, like I1 on the left and I2 on the right. And we can describe this by Lec's two equations here on the middle of the slide. In this description, the matrix elements have a clear physical meaning. They represent electrical impedance. It is easy to find experimentally the input and output impedances of the system. For systems with no internal energy sources, Z12 equal Z21. So this may be equal as this one. We assume this condition fulfilled in the remaining part of this lecture. The input impedance is the ratio between input voltage and input current. Likewise, the output impedance is the ratio between output voltage and output current. You should notice that the input impedance depends on the circuit connected to the output and vice versa. We distinguish two cases, open and short circuited terminals. The input impedance of the system in this figure is these two expressions. For the output impedance, we find the next two expressions on the bottom. Apparently, input characteristics depend on what is connected at the output and vice versa. The degree of this Marshall influence is expressed by the coupling factor K. You may see here on the bottom in the first equation, defined as this expression on the top. The coupling factor is also related to the power transfer of the system. The maximum power transfer occurs for a load impedance equal for the ZL, and we can see on the next equation. Now, we consider a piezoelectric sensor as a two-port network, analogous to the electrical system in this figure. But this time, with a mechanical input port and an electrical output port in it. In the beginning of our module, we defined the relation between stress and strain as the third line here. Similarly, the relation between dielectric displacement D, we can see here, and electrical field strength E is given by these expressions, where epsilon here is a dielectric constant or permittivity measured in farad per meters. In piezoelectric materials, mechanical and electrical quantities are coupled. A two-port model of a piezoelectric system is shown in this figure. The two-port equation of this system are in general looks like the first couple on the left. And for the linear system, in particular, in the right side of this slide. Mathematically, S in power G is a partial differentiate of S to G at constant D capital. And epsilon here is a partial derivative of D to E at constant mechanical tangent T. From a physical point of view, S capital, is a compliance at open electrical terminal when the delta T equals 0. And epsilon with power T is a permittivity at open mechanical terminal. The latter means that the material can freely deform. It is not clamped. At open electrical terminals, the voltage generated by an applied force in epsilon E equals minus GT, which explains the name piezoelectric voltage constant for G. Further, as we have seen before, the impedance of the connecting circuits, both mechanical and electrical, influence the properties of the material and hence the piezoelectric behavior. For instance, the material stiffness is higher at short circuit electrical terminals than when these terminals are open. Another set of constitutive equations is, let's see, this first couple of equations on the left side, which for linear systems becomes second couples for the E, S, and D, where S is a compliance at a short circuit electrical terminal. And D is a piezoelectric charge constant. At a short circuit terminal, the electrical displacement generated by an applied force is found to be D equal dt. which explains the name piezoelectric charge constant for the parameter d small. Other possible combinations of the electrical and mechanical quantities results in other material parameters, for instance, epsilon in power s, the permittivity as Coulomb state. Further, in literature, the parameters E and H can be found. This table shows an overview of all these piezoelectric parameters. The definitions are given as here with A as a quantity affected by B at a constant C. We will use only D and G in the remaining of this lecture. Relations between these four piezoelectric parameters follow from the respective constituent relations that define them, irrespective of which set of constituent equations is taken. They all describe the same material, and hence there is a relation between the various piezoelectric parameters. For instance, the relation between D and G is see this equation for the D as the first one. Both G and D describe the strength of the piezoelectric effect of the materials only. They do not depend on dimension. The relation between S in power D and S in power E, respectively, can be derived from the constitutive equation, as we look here, number 2. And this coupling constant is an important parameter for the strength of the piezoelectric effect. Just as in the case of the electrical system and the piezoelectric constant K, we can see here, denotes the maximal fraction of mechanical energy stored in the crystal that can be converted into electrical energy. But you should note that K differs from the overall efficiency. The equations given earlier only apply for isotropic materials, like materials whose properties do not depend on the orientation within the material. Many piezoelectric materials are anisotropic. So similar to the parameters S and C, the parameter epsilon should also be given as a matrix for epsilon. Depending on symmetry in the crystal, some of the matrix elements are zero and others have equal numerical values. As an example, this equation shows the permittivity matrices for quartz and ferroelastic Rochel salt, both respectively, and hence the dielectric properties of quartz can be described by only two parameters, like E11, epsilon 11, and epsilon 33, whereas for Rochel salt, four parameters suffice for the characterization of piezoelectric properties. Now, the relationship between E and T is described with three linear equations for D capital X and D capital Y and D capital Z, or in matrix notation. The parameters D and G too depend on the orientation of mechanical parameters. Each of the 6 force components may result in a dielectric displacement in 3 directions. So, for a piezoelectric materials, let's see next equation for D sub I, or using the notation as presented on the very beginning lecture. Next equation for DI, where the I and J measuring from 1 to 3 and K from 1 to 6. Applied, for instance, to the displacement in X direction, only in one direction. And this results in this polynomial for the T. Similar equation can be derived from D in the Y and Z directions, and for D2 and D3. In total, the piezoelectric matrix contains 18 elements. Many of them are zero due to the particular crystal structure. Moreover, many of them are partially dependent. As an example, for quartz, D12 equals minus D11, D25 equals minus D15, and D26 equals minus D11 due to the specific crystal structure of this material. So, the 3 times 6 dimatrix in the equations, as we can see in the beginning, with the numerical values, and hence the equation for D for the quartz can be written as blue for the first expression for D1. And so we may find expression for D2 and D3. As an illustration, we give here the piezoelectric D matrix for the two other piezoelectric materials, lithium, titanium, or cold ceramic, and PVDF, cold outer onyxal stranges, respectively, at these two big matrices. For a unique notation, with respect to the orientation of polarized crystals, an agreement has been made saying that the z-axis or 3-axis is the direction of polarization. And this figure visualizes various components of the D matrix. In all these examples, the electrical output, like voltage or current, is measured in the direction of the polarization vector in 3 directions. So, the components of the matrix are all of the force of D3I. In Figure 8, the applied force is in the polarization direction. Many crystals have high piezoelectric sensitivity in this direction, which explains the often encountered parameters D33 in specification sheet. This mode of operation is called longitudinal, since the mechanical and electrical directions are the same. In Figure B, a force is applied perpendicular to the direction of polarization. This is the transversal mode of operation. Transversal operation is used with crystals having these high values of D32. Figure 3 shows a shear force in transversal direction. Here the 4 directions, yielding the parameter D34. And finally, Figure D. The shear force is applied in the 6th direction, so the parameter D36 shown here. This table presents for comparison purposes the various properties of a ceramic material based on PZT, lead, zirconium, titanium, of quartz, and of PVDF. You should note that the numerical values of all piezoelectric parameters depend on the temperature, on composition, and on the manufacturing process. Piezoelectric coefficient of PVDF and a measurement method for obtaining numerical values can be found. For instance, where all piezoelectric constants according to equation are presented. From data sheets of various manufacturers, data for a modified form of lead zirconate titanate, small modifications have a large effect on most piezoelectric properties. Next lectures will be piezoelectronic sensors. And now, I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye.